Hey everyone and welcome back to Prefusion. So today we'll solve a very interesting question from control systems. So this is basically mixed question, like combination of analog electronics and control system. So someone in our group sent this question, which has been asked in interviews, like not in written test. So we will solve this question today. So if you want to know more of these types of questions, so you can join our Telegram group. I will give the link in the description, or I will pin the links in the comment. So what is this question asking us? We have been given a circuit diagram, and they have told us the op-amp has a transfer function A of S. Basically, it is a function of frequency. Now we have to find the phase margin of the given circuit. If the circuit is arranged like this, we have to find the phase margin for the given circuit if A of S is somewhat like this. Okay, phase margin in degrees, I haven't mentioned, it is in degrees. So obviously first intuition should be can you tell me intuitively what will happen? Can you tell me intuitively, if initially my phase margin was some value X, now if I connect a feedback with it, what will happen to the phase margin? Will the phase margin increase or decrease? So intuitively, what will happen here is that if I have connected a feedback, why do we connect a feedback? We connect a feedback to make the system more stable, explicitly negative feedback. We connect negative feedback to make the system more stable, right? So if you want to make the system more stable, what does this relative stability parameters mean? Gain margin and phase margin. Basically, this relative stability parameters mean that if there is some variation in my poles, okay, so currently what you're seeing, these are not the closed loop poles, these are the open loop poles. My closed loop poles will be something else that will tell me the exact stability, right? Exact stability. I'm just now doing the relative stability analysis. So if there is some disturbance in my system, then the pole's location will change. Now, how much disturbance can my system tolerate so that my system is still stable? That is what this gain margin, phase margin tells us. So how much margin do I have that the system can tolerate, that so that it can still remain in stable condition? So that is what gain margin and phase margin tells us. So as I'm adding a feedback over here and a negative feedback, so obviously the phase margin will increase now. But what is the trade-off of this? Obviously there will be some trade-off, right? So the trade-off is the gain will reduce. The overall closed loop gain will reduce. You will see the open loop gain will be higher than the closed loop gain. Okay, so obviously you have to balance between these two. That is why we learn all this, right? In control engineering, exactly that is what we learn. So that was a brief overview. So I will just give you a brief overview about the parameters of relative stability. If you want to learn all this, right, I have taught full control systems. You can go to the playlist. I will give the link of these lectures and you can watch those, right? So trust me, no one in YouTube has taught that type of content, that depth of content of control system, right? Everyone will teach you the basic things and they will go away. Okay, so yeah, you can watch that playlist. I will put the link in the comments below. So what is gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude of the OLTF becomes 1. Simple, a name suggests itself. Phase crossover frequency is the frequency at which the phase of the OLTF becomes -1. What is OLTF? OLTF is a feedback system like this, right? So if you know the feedback system, so this is like a feedback system, and OLTF is G into H of S, basically the feedback into the open loop gain. So here, what is our feedback? Can you tell me what is our feedback? You might say, sir, beta, all those things. If you don't, if you are not able to remember beta, all those things, right, you just simply apply the rules of KCL, KVL. So feedback means how much portion of this output is getting mixed here to the input. Basically, this is like a resistor divider because no current is flowing through here, right? No current is flowing through here. Infinite impedance, infinite input impedance of the op-amp. So this will be here. The voltage will be V out, 4 V out upon 5. Simple voltage divider, and 4/5 portion is getting added with V in. Exactly that is what I have drawn over here. So your beta will be simply 4/5. So if you are not able to remember the formula, don't remember the formula. You apply simple KCL, KVL. Okay, you don't, it's impossible for us to remember these many formulas. अगर इतने सारे formulas याद करोगे तो मतलब एग्जाम हॉल में पागल हो जाओगे. तो कुछ बेसिक चीज़ें याद करो ताकि वो आप रिकॉल कर पाओ और वो आप एग्जाम हॉल में सॉल्व कर पाओ. सो ट्राई टू सॉल्व एज मच एज पॉसिबल एंड रिमेंबर एज लिटिल एज पॉसिबल, क्योंकि बहुत सारी चीज़ें अभी याद करनी है आपको, सिर्फ एनालॉग कैलकुलेशन नहीं. जब सारे सब्जेक्ट एक साथ करोगे तो बहुत सारी चीज़ें हो जाएंगी. तो इसलिए ऐसा करो कि जो एकदम मतलब याद नहीं करना ही है उसको ही याद करो और बाकी चीज़ों को डिराइव या ऐसे करके याद करो, केवीएल केसीएल यूज़ करके याद करो. ओके, सो सॉरी फॉर द इंग्लिश व्यूअर्स, आई स्पोक इन हिंदी. सो द फीडबैक बीटा विल बी 4/5. So what we like, I will talk about the voltage later on. So this is talking about the voltage, right, where my phase of the voltage becomes -1, -180, and this is 1. Now, like, what is margin? What is gain margin? Gain margin is basically the reciprocal of the magnitude of OLTF at phase crossover frequency, and phase margin is basically the addition amount of phase lag that needs to be added to the phase of the system at gain crossover frequency. The formula is given like this. I will not explain this here too much because I have explained this already in my lectures, so you can go and watch those there. I just wanted to give a brief overview. Now, few students get confused that like, you can see the transfer function of this, right? So you might say that sir, we can apply the dominant pole concept, because we know that if like the two poles are very far apart and one pole is very near to the origin, which is this, right, and the other pole is very further away from the origin, we can ignore that pole. Now, when studying the dominant pole concept, you have to remember why did we ignore that pole. Like, I will just give you a brief overview why we won't use dominant pole concept here. Because just remember, I derived this in my lectures, I'll put the link. Just remember that these two poles are very further away. This is more nearer to the origin, this is further away from the origin. Now, when I draw the impulse response of this, like when I compute the impulse response, what do I see is this one is for the first pole and this one is for the second pole. This response is coming for the second pole, right? Now, what do I see? As the time passes away, the effect due to this, right, is very minimal. Effect due to the second pole is very minimal. So if the effect due to the second pole is very minimal, even if I ignore this, right, even if I ignore this, I will, like, my response, time response will be almost same. So if ignoring this makes the time response same, that's why we ignore this and we just compute with the pole that is nearer to the origin. Okay, so it was for the time response, not for the frequency response. So you don't use dominant pole concept in frequency response. So don't get confused with this concept, right? So dominant pole concept will be used only when you can ignore the when you're talking about the time response. So it is very important to understand that concept. Now, like, here I've mentioned few points about dominant pole. You can read these things. The main thing is, if the ratio of the significant pole, that is pole near to the origin, to the insignificant pole is more than 4, then you can use the dominant pole concept, but only for time response, not for frequency response, because we are analyzing frequency response now. We are not concerned with time response, and dominant pole concept came only due to time response, because the time response was almost same with that pole that is further away from the origin and without the pole. So that's why we ignore that pole, because that will just increase our computation. So this is the first thing. So we can't use dominant pole concept. So let's come back to the question and let's solve the question. So beta is 4/5 and my A of S is this, right? I will copy my A of S. Now everything will get copied, I think. Yeah, I knew this. So this one I can delete. Okay, my E of S is this. So, like, basically, what is my OLTF? Can you say what is my OLTF? My OLTF is simply like I was already drawing this again, the feedback factor on those things. So I hope you know the feedback factor. Basically, the input impedance here is infinity. So this is act like a series circuit, and here voltage divider will act. So basically, my OLTF, which is G of H of S, will be simply this multiplied by this, right? A beta. So which is in our case 32, and I will just copy this. Okay, by this, and let me write it in terms of frequency, right? In terms of frequency, because in frequency domain, what do? We replace S equals to j omega. So this, all this will be replaced by S equals to j omega. Now, one good thing you can do, like, to reduce your computation burden, that you assume at starting itself that omega is in mega radian per second, because this question is calculative and you have to understand how to calculate things, right? These things. So you have to take shortcuts. So you assume omega is mega radian per second, then obviously this 10 raised to power 6 and this 10 raised to power 6 will be gone. Okay, because we have assumed it mega radian per second. So like, this 10 raised to power 6 will be gone, and it will help us in computing the value of phase margin. So for phase margin, what is the case? We have to find first we have to compute the angle of the OLTF at omega equals to omega GC, that is when my gain becomes 1. So obviously we have to find the frequency at which my gain becomes 1. So for that, my magnitude of GH of j omega at omega equals to omega GC will be 1. Okay, which is equals to this, right? 32 by under root 1 plus omega square into 1 plus omega 40 square. Okay, so like now to solve this, how will you solve this? So this becomes a bit difficult to solve, so you assume omega square to be x and then you square both sides. So omega square is x, this will be 1 plus x into 1 plus x by 40 square equals to 32 whole square. Now you just see how am I computing this, right? It is very important because like if this question comes from gate or some other exam written test, right, you have to understand that you have to solve this as quickly as possible. So you have to understand how to solve it as quickly as possible with minimum error. So what you do, you write this 1 plus x into 1 plus 1 by 40 square plus x square by 40 square equals to 32 square. So now you have to take approximations. So this 1 plus 1 by 40 square, like 1 by 40 square is so low that it will be only 1 here, and if I do 32 square, subtract 32 square with 1, it will be exactly equal to 32 square, right? 1 is insignificant, so I can ignore these things. So this equation will become x square by 40 square plus x minus 32 square equals to 0. Now obviously we'll use the Sridhar Acharya formula. So we'll compute x will be equals to minus 1 plus minus b square, b is 1 square. Now minus 4 AC, here we have already a minus, so it will be plus 4 times 32 square times what, 1 by 40 square. So a is 1 by 40 square, keep that in mind, and divide by what, 2a. So this will be 2 times 1 by 40 square. So now you can compute this, right? So I have already computed it, I will just compute it in front of you again. So 4 times 32 square divided by 40 square plus 1 and under root. So it will be 1.18, 1.887. Now will I take the plus positive sign or minus sign? I will take the positive, because obviously x can't be negative because omega is not imaginary, right? So I will take the positive sign only. Minus 1 divided by this 2, and obviously I have a 40 square. Okay, 40 square here. Okay, I don't have enough space. So what will be this? If I subtract 1, then I divide by 2, then I multiply 40 square. Okay, this will be 709.437. This is x, this is not omega, right? What is omega? Omega will be x equals to omega square, so omega will be under root x. So if I take the under root of this, okay, no, oh no, 709.437 under root is 26.63 radian per second, mega radian per second. Okay, this is not radian, this is mega radian per second. Okay, so obviously this is my omega gc, gain crossover frequency, or g, whatever you want to say, omega g or omega gc. Now obviously let's come to the interesting part, right? The phase margin. So phase margin is simply 180 plus, now why does 180 get added, and like all the reasons, right, I've explained in my lecture, so you watch the lectures. Angle of g of j omega, h of j omega at omega equals to omega g. So this is 180, and what is g of j? Like this 32 is insignificant, right? This 32 is insignificant, so these are in tan inverse format. So this will be minus tan inverse omega minus tan inverse omega by 40. So like at omega equals to omega g, so I will replace this omega with omega g. Okay, replace this omega with omega g. So this is 180 degree minus, now omega g was how much, 26.63, right, or 26.63. so 26.63. do take care of degrees, radians, all those things in your gate calculator. It will be very important. Tan inverse So this is minus 87.85, and this is 26.63 divided by 40, tan inverse 33, so this will be minus 33.654. all these are in degrees. So now if I subtract, or this will be plus, right? It will be plus 87.85, and if I subtract this with 180, this will be almost 58.47, right? 58.47, 58.5, almost 58.5. okay, 58.5. like there can be bit of approximations here, so you can like check if your answer is coming a bit different. You can check that. So this is my answer. Okay, 58.5, this is my answer. Now what you do, like you got your solution, the students who came for the solution, this is a solution. Now what I want to do, I want to compute the phase margin for open loop system. Generally phase margin is defined for closed loop system only, because we want to check the relative stability parameter, which system has better stability parameters, right? But let's check whether it is true or not. I explained with you with intuition, right, that if I add a feedback, then the phase margin will increase, system will become more stable. Let's check that and compute the relative stability parameter for this. So let's compute the gain margin for this. If I have a open loop system, so if I have an open loop system, then my like g of j omega will be simply this 40 upon this, right? So this is equals to my OLTF. My OLTF becomes this, h is 1, so this is my g of s. So if I write my g of j omega, again I will define my omega equals to in mega radian per second. So this is 40 divided by, I want to compute the phase margin for this open loop system, 1 plus j omega into 1 plus j omega divided by 40, and obviously my omega is in mega radian per second, right? Okay, so this I need to change this, but this will not be equals to, this will be something like this. Okay, so this will be simply, now if I want to compute the magnitude and equate it with 1, so this will be 40 by 1 plus omega square, 1 plus omega square by 40 square. Okay, so obviously I will again assume x equals to omega square, so this will become 1 plus x into 1 plus x divided by 40 square equals to 40 square. So what I can do, again do the same approximation, right? If I do the same approximation, this will be 1 plus x into 1 plus 1 by 40 square plus x square by 40 square equals to 40 square. So your x square by 40 square plus x minus 40 square equals to 0. So your x will be minus 1 plus minus b square, that is 1, minus 4ac, this is plus 4 only, because 40 square into 1 by 40 square will be 1, and I have 4ac, divided by 2 into a, which is 1 by 40 square. So this will become x equals to 40 square into root 5 minus 1. Obviously we will ignore the negative solution, so if I do the root 5 minus 1 divide by 2, it is 0.618, right? So it will be almost equals to, if I do 40 square, 988, okay, 85, and if I do take the under root of this, so my omega g dash will be 31.44 mega radian per second. Okay, so omega g dash is 31.44 mega radian per second. So if omega g dash is this, now you can compute your phase margin. Again, phase margin will be that same formula only, 180 plus angle of j omega at omega g. So I will directly compute this 31.44, and okay, this is plus only, yeah, this will be minus, actually minus tan inverse 31.44 divided by 40. So this divided by 40, if I do, then take the tan inverse, this will be minus 38.173 degrees, and if I do 31.44 tan inverse, this will be 88.18 degrees. Okay, and if I do 180 plus this, so this, if I add this with 38.173, then do subtract, then plus 180, you can see my initial phase margin was 53.65, almost nearly 53.65 degree. So my phase margin was initially this if I had only the op-amp. Now if I add a feedback, my phase margin increased, the margin increased. Okay, you can anyways understand it from here itself that your OLTF, this, right, like DC can reduce, okay, that means it will reach to unity gain faster. Okay, because for lower value of omega it will reach to unity gain. Now for if low angle, like if the value of omega is lower, then obviously this phase lag, right, this phase lag will be lower. If this phase lag is lower, then whatever I add with it, like this will be greater, phase margin will be greater than the case, like the open loop case. Okay, and if you want to cross verify, right, whether the omega g you calculated is correct or not, just simply put this omega g in this equation. Just simply put this omega g in this equation, and you observe that whether you're getting very near to 1 or not. So it will not be exactly equals to 1 because we have made approximations, but it will be nearly equals to 1. So whenever you are in confusion and you have made long calculation, right, always, like if you are unsure, you can back calculate. You just put this omega g value here and check whether your value, whether this magnitude is 1 or not. Okay, 1 or not. So if it is 1, near to 1, so obviously you solve it correctly. So that is it for this question. I I can say for sure that no one will analyze this question like this. So I have also written it here, the analysis, right? So in both cases, in this case, like the phase margin was a bit different, was almost like 58 point something, 58.5, 58.5. Okay, I have analyzed every parameter. So obviously it doesn't change the gain margin. Like if the DC gain is changed, it doesn't change the gain margin. Okay, but it will change the phase margin. It will change the phase margin because omega PC also doesn't change. In this case anyways, the omega PC and GM are infinity because it never reaches to minus 180 degree. It reaches to minus 180 degree at infinite frequency. So it doesn't matter. But anyways, if I am not changing the gain, right, then phase crossover frequency won't change. But obviously gain margin will change because the gain itself has been changed, right? That will change, but phase crossover frequency won't change. I've analyzed this bit by bit in my playlist. You can go to there and check all this, right? Frequency response. Let me tell you, it has been taught in the best manner in this whole YouTube, right? No one has taught in that depth. So yeah, you can see that what is the omega GC and how is it varying. So for open loop system, omega GC was higher, it is lower, okay, for closed loop system, and phase margin is higher for the closed loop system. Both are stable, but this is more stable, relatively more stable. Okay, so yeah, that's it for this lecture. And if you have any more questions, you can send it to our Telegram channel, and I will see you in the next video. Thank you.